with the last lecture, right? So we will discuss about this conduction today, right? So as you know, you are already aware, right, that heat has three modes of transfer, right? Conduction, convection, and radiation. So basically, in conduction, what happens is the transfer of energy takes place, right, from more energetic particles to less energetic ones, right? And it happens in all this solid, liquid, and gas. This, right? This conduction takes place in all solid, liquids, and gases. So what happens in liquids and gases is in this particular case, the collisions and diffusions of molecules, right, takes place, and because of that this heat transfer take place, right? So here, in case of this liquids and gases, collisions and diffusions of the molecules during the random motion. This is the main reason for conduction in liquids and gases. While in solids, what happens is in solid, actually, vibrations of molecules in lattice, right, and the energy also transport by free electrons. So in case of solids, you have combined effect of that vibration of the molecules in a lattice plus that energy transport by free electrons. So this is the actually energy carriers in all this media, right, whether it is solids or it is liquid and gases. So this is how conduction takes place in solids, liquids, and gases. Now if we think about this rate of heat conduction, then rate of heat conduction basically depends on rate of heat conduction is proportional to the area through which this heat transfer is taking place, and then temperature difference, right, and it is inversely proportional to the thickness through which it is getting transferred. So this is generally this rate of heat conduction, right? And if you write the Fourier's law, which defines this heat conduction, then you will have constant of proportionality, right? That is K, that is nothing but thermal conductivity, right? So it is nothing but this Ka delta T by delta X. So if you take this delta X tends to 0, then you will have this minus Ka dt by dx. This is how this heat transfer is given in this particular conduction, right? This dt by dx is nothing but temperature gradient, right? And this equation is nothing but Fourier's law of heat conduction. So this is how you can have this heat conduction, basics of heat conduction, right? Here in this figure, as you can see, this is the thickness through which heat is transferring, right? And it is the temperature difference, right? and here the area which we need to consider. So all these things are mentioned here, and this is the heat conduction rate, right, that is mentioned here. So actually K is very important, because if you see the effect of K, then here in this particular figure, if you see copper and silicon with different thermal conductivity of this 401 volt per meter degree centigrade and 148 volt per meter degree centigrade, what happens is, if you keep temperature same in both the case, if you keep the temperature same in both the case, right, and you are also keeping this thickness same, right, so if you check the heat transfer rate, then it will be higher in case of copper, because it is having higher thermal conductivity. So this is how thermal conductivity shows the capacity of a material to transfer the heat through that particular material. Now we will go for this different cases, right, and we will consider 1D heat conduction only, as it is mentioned here, right, and we will see various shapes or various walls through which it is going to transfer. Here we are considering a large plane wall, then we will see cylindrical wall, and then spherical wall. So if we see this 1D heat conduction in all these three one by one, then let us first see, as shown in this figure. Here area is considered as same at both the place, right? We are considering this element basically, which is highlighted here, right? This one. So we are considering this element. So if we write heat conduction equation for this particular element, then how we can write it is actually this rate of heat conduction at x, rate of heat conduction at x, right, minus this rate of heat conduction at x plus delta x plus delta x, right, plus rate of heat generation inside the element, right. It may happen that some heat may be generated, right. For example, while transmitting current through a particular wall, there is a heat generation I square R, right. So it may happen in some particular equation or some particular situation, heat may be generated. So this rate of heat generation inside the element. So this is particularly, you can equate this to rate of change of energy, right, contained in the or whatever the energy is changed in that element, right. This rate of change of the energy of that element, right. So basically, rate of change of energy content in this element is given by the heat entering and heat leaving, right, plus this actually rate of heat entering minus rate of heat leaving plus energy generation. That is the rate of change of energy content of that particular element, right. Because if you consider this element before the entering of this energy and leaving this energy, then it will have only this energy which is generated inside this element. So basically, whatever heat is transmitting through that element, it is changing the energy inside that element, and that is given by this relation. So if we further write and simplify, then this qx minus qx plus delta x, right, qx minus qx plus delta x plus this generation, right, as we have discussed, will be equal to this delta E of element per time, right. We are considering the rate. So once you have this, then you can actually further simplify this generation of heat and the rate of change of this energy. So how you can simplify it? If you first simplify this rate of change of energy, then it is at t plus delta t there will be some energy, and at point t some energy will be there, which is given by this mc delta t, right? It is at t plus delta t and at particular time t. And c further can be m further can be written as rho into v, right? Rho into v is nothing but rho a delta x in our case, because a delta x is the volume of our element. So this is how you can write this delta E, right, for this particular case. Similarly, the generation of energy can also be mentioned with this let us say this is energy generation per unit volume, and we can multiply it with this volume A delta x as we have seen above, right? So if you put all these values in the above equation, then you can simplify that equation as this qx minus qx plus delta x plus G A delta x be equal to rho C A delta x, this T, right. So this is how you can simplify it, and here also you can divide it by this volume. So if you divide it by volume, then you will get this equation, right? So now if you consider this limit delta x tends to 0 and delta t tends to 0, then you can have it in terms of your differential equation, right? So here it is 1 upon E del by del x. This del q by means the rate of heat generation, we can equate it to Ka dt by dx, right? So I am directly putting it here, as we have seen that heat conduction is given by Ka dt by dx. So this is how you can have your differential equation of heat transfer in 1D for this plane wall, right? Now here you can apply various conditions, right? For constant conductivity, let us say constant conductivity, you can take this K out, right, because it is constant. So for that particular case, you can have your equation modified. Area we are considering constant only, so it will be anyway nullified, right? So here if you consider K as constant, then your equation can be modified as del square T upon del x square and plus this generation of heat divided by K plus this rho C by K del T by del T. Here basically thermal diffusivity is defined as this K by rho C. So further simplification can be given as 1 upon alpha delta T by delta T. Now once you have this equation, right, which gives 1D heat transfer in plane wall, then you can consider different case here also, that if it is steady state, then change with respect to time will be 0, right? So you can write in that case that del square T upon del x square, this G by K is equal to 0. Now in case of transient, if we are considering no heat generation, right, transient and no heat generation, then it will be this del square T upon del x square is equal to 1 upon alpha del T by del T, right? Yeah, this T is temperature, this T is time, right? So, and if we combine this, that steady state plus no heat generation, steady state plus no heat generation, then it can be written as del square T upon del x square is equal to 0, or you can write this T square T upon dx square is equal to 0. This is how you can have your relation in case of this plane wall. Now if we go for a long cylinder, let us see how we can have this heat conduction. Yeah, so here for this long cylinder, as you can see in this figure, now what is going to happen is your area is now going to change, right? Area is 2 pi RL. So if you consider all those things which we have considered in the previous case, then you will come up with something like this, right? I am directly writing this. So now again here this is given by Ka delta T by delta R, right? So we can simply write Ka delta T by delta R plus this heat generation, right? And here now you can put this A is equal to 2 pi RL. So if you put A is equal to 2 pi RL, then you will have this 1 upon R del by del R Kr delta T by delta R. Otherwise means all the constant will be anyway cancelled, right? 2 pi L. So here it will be saying that G and this OC del T by del T. Now for constant conductivity, again you can have this 1 upon R del by del R as we have done earlier, right? Rho C by K I can directly write as 1 upon alpha right. So this is how you can have your equation for cylinder, right? And here also you can apply all those steady state, transient, and steady state plus that transient. So if I write those equation, then actually for steady state it will be like this simple, right? That and for transient and no heat generation, right? And if you combine both steady state plus no heat generation, then you will have this 1 upon R this here it is del by del R del T by del R equal to 0, right? So this is how you can have and this r can be also taken this side, so it is only this del by del r del t by del r, right? Or you can say exact differential also, because here only this variable is there, right? Yeah, so this is how you can have for this cylinder, right? As it is mentioned, for long cylinder you can have this as 1D heat conduction equation. If you go for 1D heat conduction equation for a sphere, then your area will be 4 pi r square, right? So it is all similar only. So for a sphere I am directly writing for this particular case where we are not considering that conductivity is constant, so at that time we can represent it like this, right? When you consider constant conductivity, then you can have this 1 upon r square right. And for again steady state, it will be like this, and transient no heat generation, so this again can be reduced to this d by dr r square dt by dr equals to 0. So if you further simplify this, then you can write the differentiation of r square and dt by dr 1 by 1. So if you first go for differentiating dt by dr, then it will be like this. Then if you are going to differentiate r square, then it will be like this, equal to 0. So finally you can have this r t square t upon dr square plus equals to 0. So this is how you can have the heat conduction equation for 1D, right? In case of sphere, right? So we have seen all these three different cases, right? You can also write a combined 1D heat conduction equation for all these three, right? It will be something like this. Right, and here you can have different case of this generalized equation, as n equals to 0 will give you for plane wall, n equals to 1 will give you a cylinder, and n equals to 2 will give you a sphere, right? Heat transfer or heat conduction through a plane wall, cylinder and sphere. Now we have seen this different case according to the shape of that wall. Now if we go by coordinate system, then we can also write this general heat conduction equation, right? Considering all this direction as it is mentioned here, we are considering this volumetric element, right? So suppose if we go for if we first go for this rectangular element, right? And this too can then directly be derived once we are done with this general heat conduction in rectangular coordinate. Then this is you can define it easily. We will see how x, y and z is going to vary in this cylindrical coordinate and spherical coordinate. First we will see it through rectangular coordinate, right? So if we go for this rectangular coordinate, right, this general heat conduction equation, So now here what is going to happen is rate of heat conduction at x, y and z. So here if you consider that element again, so you are here having this three different heat entrance, right, at x, at y and at z, right. So as we have consider over there, only in 1D you are considering only one, here you need to consider this all three, right. So if we modify that 1D to this general, then it will be this qx plus qy plus qz, right, minus this qx plus delta x, qy plus delta y and qz plus delta z, right, plus whatever that generation was there, right, in element, and there is a change of energy in that element, right. So again here also you can write this delta E element is equal to Et plus delta T minus Et will be given by this MC T plus delta T minus Tt, and this now here your M will be that rho into volume, and volume here is rho delta x delta y delta z, right. So this is how you can have your this delta E. Similarly for this generation of heat, you will have this G into volume of element, right, as we have considered previously also. So this is how you can have your different values of this G and delta E in this case. Now if you put all this value in that equation, and if you give a simplification, right, and you consider that area for x will be the delta y delta z, area for y will be delta x delta z, and area for z direction will be delta x delta y, right. If you go and check that element, then you can have idea, right. For this z direction, if you consider, the area is delta x into delta y. Similarly for other, it is this delta x delta z in case of y, right, and in case of x it is delta x delta y, sorry, delta y delta z. You can see as for z it is delta x into delta y, for x it is this delta y into delta z, right. And if you go for y and verify, then for y it is this delta x and this delta z, right. Are you getting what I am saying? Hello.
Yes, sir.
Okay, so for
Yes, sir.
so for this, all this you are having this areas, right. So if you consider all this area, and if you put all the above values in that equation, and if you consider that q x plus delta x minus q x over delta x is nothing but ka delta t by delta x, which we have considered while 1D heat conduction. So I am skipping some of the steps and I am directly writing. You will get something like this if you put all those value and give simplification. Then you will have this equation, right. Now for constant conductivity, here also you can simplify. Right, you can simplify it to this equation if conductivity is constant. right? This is known as Fourier-Biot equation. Now here also you can go on providing those situation which we have considered for 1D heat conduction, right? What you can do is you can check how it is going to vary if you are considering steady state. In case of steady state, it will be like this. Right? So this is known as Poisson's equation. If you consider transient and no heat generation, right? And if you provide both steady state and no heat generation, actually this equation is diffusion equation. And if you go for a steady state no heat generation, so you will find it as this one. Right, so this is how you can have your heat conduction or general heat conduction equation when you are considering all these three direction. Now for cylindrical and spherical coordinate, I am simply writing cylindrical coordinates. You will have your x is equal to r cos phi, y is equal to r sin phi, and z is equal to z. So for that you will have some thing like this. If you provide all those equations and give simplification, then it will be like this. Right, and for spherical coordinates, your x is r sin theta cos phi, y is r sin theta sin phi, and z is equal to r cos theta in case of spherical coordinates. So for that you can have your equation something like this. Right, so this is how you can have your heat transfer or heat conduction equation, right, for all three direction in this different coordinate systems. So once you have idea about this, then you can go for steady heat conduction for plane walls. So as you already know a little bit, right? In this case, your Q conduction through wall is simply represented by this minus Ka dt by dx, right? So if this is for this particular element, if you are going to integrate it over whole, then it is 0 to x, and then temperature will be T1 to T2, right? As you can see here, T1 to T2 is the temperature, and this dx is going to what you can say, integrated over 0 to x. Now this dx I am taking this side, right? So if you integrate it, then what you are going to get is this Q conduction through wall will be Ka T1 minus T2 divided by L, because here dx is x and 0 to x is this L minus 0, that is this L length, right? So Ka T1 minus T2 by L. Now this conduction through wall is actually analogous to this current transfer through this resistance, right? So with this analogy, if you consider that driving force here is temperature difference, here driving force is this voltage difference. So here in this case of heat flow, the driver is this T1 minus T2, right? So resistance will be this T1 minus T2 upon R. So R will be L upon Ka in case of this conduction through plane wall. So if I provide or use this analogy, then I can write this Q conduction through wall is equal to T1 minus T2 over R wall, where R wall is nothing but L by Ka, right? So here actually the series in parallel is also applied. As for resistance, we are applying series in parallel. Here it will be added if it is in series, then it will be that R equivalent will be equal to 1 upon R1 plus R2 if it is in parallel, right? For parallel. Here it is in series, so it is directly added. So for convection, you know that is 1 upon HA is resistance, right? So if it is transferring, then there will be convection in this region, then conduction here and convection here. So total resistance will be added, right, as it is mentioned here. So this is how you can have your addition of what we can say, this resistance, right? Now if you go for this steady state conduction in the cylinders and spheres, then it is also, as you know, for cylinder, if we say this Q conduction for cylinder is nothing but minus Ka dt by dr. So if you integrate it over R1 to R2, Q conduction for cylinder into dr over A, right, will be equal to T1 to T2 K dt. Now A here in this case is 2 pi RL, so it will be 1 upon 2 pi L 1 upon R Q conduction for cylinder dr equal to this minus K T2 minus T1. So if you simplify this as it is R1 to R2, then finally you will get that Q conduction for cylinder will be given by this 2 pi KL. Here I am changing it T1 minus T2 because this negative sign is there, and this ln R2 by R1. So this is how it is given in case of this cylindrical. As we have seen earlier, if we go for this resistance of this cylinder, then you can write that R cylinder is equal to this ln R2 by R1 upon 2 pi KL, right? And now finally if we go for this spherical case, for spherical you can have this integration R1 to R2 Q conduction for sphere. Area will be 4 pi R square in that case. So if you give simplification, then you will find Q conduction for sphere is coming about this. Because 1 upon R square will be minus 1 upon R, right? Here in that integration. So you will find this for this sphere. Here also you can write that again T1 minus T2 upon R sphere, right? So R sphere is nothing but R2 minus R1 upon 4 pi K R1 R2, right? So this is how you can have your resistance for all these three different cases and heat conduction through all these three different types of wall. Now one more important thing is this critical radius of insulation. We will see this concept and then we will solve some of the gate questions. Here insulation means we are generally adding insulation in order to reduce the heat transfer. So in case of plain wall, it is fine. If you are going to add the insulation, then length is going to increase and resistance will increase and heat transfer is going to go down. But in case of the cylindrical and spherical, it is not so, because when you are going to add cylindrical surface, this conduction is going to increase the resistance, but at this phase, this particular convection, for convection, larger surface area will be available, right, for convection. So it may happen that this heat transfer may increase, as you can see in this case. Without insulation, this is heat transfer. Now if you are adding the layer of this insulation, then up to this radius, it is actually increasing instead of decreasing, right? After that it will again decrease, but we must have to increase material beyond this critical radius of insulation. Then only we will be able to reduce the heat transfer, right? So this is how we are having this concept of this critical radius of insulation. So as it is mentioned here that this resistance of insulation and resistance of this convection, if we write heat transfer equation for that particular cylindrical case, then it can be this T1 minus T infinity is the difference, as you can see in or observe in this particular case. Here it is T infinity and here it is T1. So this T1 minus T infinity is your temperature difference, and then you can have this R insulated and R this convection. So if you further simplify this, then it is T1 minus T infinity ln R2 by R1 2 pi Lk plus 1 upon H 2 pi R2 into L, right? Because it is 1 upon H into A, and this we have just now seen for conduction ln is for conduction resistance is ln R2 by R1 upon 2 pi Lk for cylindrical case. So what happens is, in order to find that particular place where that this slope is 0, what we need to do is we need to differentiate this Q with respect to R2, right? This is your R2. What should be the R2 in order to get this maximum heat transfer, right? And we need to go beyond that in order to reduce the heat transfer. So if I go and differentiate this with respect to R2, then basically I need to differentiate this only because, and that too with negative sign, because the T1 minus T infinite is not going to vary with R2, and we are equating it to 0, so this denominator square is going to anyway multiply with 0. So what I basically need to do is I need to differentiate this with respect to R2. Right. So if you do this, then you will come to know that your R critical for this cylinder is K by H, and if you go for spherical shape, then for that R critical for this spherical shape is given by 2K by H. Right. So here R critical for spherical shape is given by 2K by H. So this is how you will have your what you can say this critical radius of insulation. So did you get this one, that you need to increase radius of insulation beyond this point, otherwise there will be increase in heat transfer instead of decreasing heat transfer. Are you getting this?
Yes, sir.
Okay, okay.
Sir, what is the reasons for heat generation in the plane wall cylinder?
Sorry,
What is the reasons for heat generation?
rate of heat
In,
generation, huh?
heat generation in the plane walls.
In the plane wall, right? This one,
No, G not.
this one, right? So actually what happens is sometimes you may have some elements in which heat may be generated. As I have given example, that if you are having a conductive wire and you are transmitting electric current through it, then if they are at different temperatures, then the heat transfer will take place according to the temperature difference, but at the same time you also need to consider the heat generation within that element, which will be proportional to that I square R if it is transmitting this current. Are you getting what I am saying?
Yes, sir.
Okay, so now let us see some of the questions from GATE. So this is one-dimensional unsteady state heat transfer equation for a sphere with heat generation at the rate of Q can be written as. Can anyone tell the answer? It is a straightforward
B.
question.
B.
B will be the answer, correct. Now if you go for the next one, a stainless steel tub of 2 cm ID and 5 cm OD is insulated with 3 cm thick asbestos. If the temperature difference between the innermost and outermost surface is 600 degrees centigrade, the heat transfer rate per unit length is. Can you try this one by yourself? Hello?
Yes, sir.
Okay, okay. Try this one and let me know. Here if we go for the given data, then K is given as 19 watt per meter Kelvin. Right, stainless steel, it is 19 watt per meter Kelvin. And you are given the ID and OD, right, of this particular R1 and R2, this this particular cylinder, this is Ks, and then you are having this layer of asbestos Ka, right? So that you will have your R3, right? Here you will have inside temperature, here you will have outside temperature, and then heat transfer will be there, right? Q. Now let us see this diameter D1 is given as 2 centimeters, right? So R1 will be 1 centimeter. If you convert it to meter, 1.01 meter. Similarly, D2 is given as 5 centimeter. So R2 is 0.025 meter. Now this thickness is given as 3 centimeter. So R3 is R2 plus this T. So that is 0.055 meter, because 3 centimeter is 0.03 meter. So Ks is 19 watt per meter Kelvin, while Ka is 0.2 watt per meter Kelvin. Now Ti minus To is given as 600 degrees centigrade. Now what you need to calculate is Q per unit length, right? So if you write first heat transfer equation, then it will be Ti minus To upon R. Here R will be the conduction through the steel as well as conduction through asbestos. Here we are not considering that convection, only conduction is being considered. So that R is R steel plus R asbestos. So as you know, in this particular cylindrical shape, we are having this as a resistance equation, Ln R2 by R1 2 pi KSL. Length is same for steel and asbestos, right? And here it is Ln R3 by R2 2 pi KAL. So L you can take common, and then it will go to the numerator, and then you can write Q by L directly, right, which is asked, that heat transfer per unit length. So if I put all these values and I directly write Q by L, that is this Q which is asked, then it is 600, that is Ti minus Tu, then 1 upon 2 pi Ks, 2 pi Ks is 19, and Ln R2 and R1 we are having 0.25 and 0.01. This 1 upon 2 pi, this is 0.2, and again Ln 0.055 by 0.025. Yes, if you are going to simplify this, then you will have your answer. Can anyone tell me the answer?
944.
Yeah, it will be around 944
72 watt per meter.
per meter. Yeah, so everyone is getting this same, right? This one. Everyone is getting the same?
Yes, sir.
Okay, okay. Now to go for the next one. Yeah, here heat flows through a composite slab as shown below. The depth of the slab is 1 meter. The K values are in watt per meter Kelvin. The overall thermal resistance in this Kelvin per watt is. So, can you try this one? Hello. Here your circuit will be like this, right? So R1, R2, R3 will be like this. As this is a plain wall, your this resistance will be L by Ka, right? This R will be L by Ka. So for all these three, first you can calculate R1, R2, R3. Then your total resistance will be R1 plus this R2, R3 upon R2 plus R3, because here it is in parallel, right? So for parallel, it is 1 upon R2 plus 1 upon R3. Okay, are you getting it? Hello?
Yes, sir.
Okay, okay.
28.8.6.
28. Okay, correct. Anyone else? Anyone else got the same answer? So if we write all this resistance one by one, then R1 is delta 1 upon K1 A1. So delta 1 is this 0.5 length, right? And K1 is 0.02. Area is given here, right? This is 1 meter by 0.5, sorry, it is 1 only, right? So here area is 1 into 1, right? And this K1 is 0.02. So this way R1 is 25 kilowatt. Correct? Yes or no? Hello?
Yes, sir. Yes.
Okay.
Yes, sir.
Yeah, so this is for R1, right? For R2 and R3, area will be 0.5 into 1 and then 0.25 into 1, right? So let us write all one by one. So R2 is equal to this delta 2 by K2A2. Delta 2 is nothing but 0.25, right? Delta 2 and delta 3 both are 0.25 only, right? And for both, area will be this 0.5 into 1, 0.5 into 1. So 0.5 will be area for both of them. So here I am writing only 0.5 into K2 is given as 0.1. K2 is given as 0.1. Let us see. K2 is 0.1, right? And then K3 is 0.04. Okay. So R2 is 5 kilowatt. Yes or no?
Yes, sir.
Similarly, this delta 3 by K3 A3 will give you 12.5 kilowatt. So once you have all this, then total R will be given by, as we have discussed, it is R1 plus R2 R3 upon R2 plus R3 is equal to 25 plus 5 into 12.5, 5 plus 12.5, so that is 28.6 kilowatt. So all of you are getting this? Hello?
Yes, sir. Yes.
Okay. So let us go to the next one. Yeah, in a composite slab, temperature at the interface between two materials is equal to the average temperature at the two ends, assuming the steady one-day heat conduction. Following statement is true. Can you try this one? It is very simple, right?
Yes, sir.
Please try. So for steady state heat transfer, heat transfer through slab 1 is equal to heat transfer through slab 2. So here K1A, this
Sir,
T1
K1 equal to
minus
2K2.
sorry.
K1 equal to 2K2.
Okay, let us check. Yeah, it is correct. So let us check. K1A T1 minus T
Sir,
meter upon 2B.
sir, I have noticed that for this kind of problem, always this
Sorry.
T2 part is sir. I have observed one thing for this kind of problem. T2 always like uh, uh, get like double or triple according to the distance of the plate or slab.
Uh-huh.
Like in that relation, K1 equal to 2K2 here, if the distance would be the 3B, then it might be like 3K2, this kind of things, sir.
Yeah, yeah. It may be K1 equal to 3K2 then.
Yes, sir.
Yeah, yeah. Here T inter is T1 plus T2 by 2 is given, right? Because it is assumed that this is average temperature at the two ends, right?
Yes, sir.
So once you put all this value, then you will find your
So,
K1 is equal to 2K2,
sir,
right?
in your opinion, sir, in GATE, then we shouldn't like solve this kind of problem. So, as per assumption, so this is as I have observed this kind of thing. So, could we answer it directly, or like you will prefer
See,
to go for?
you need to read the question thoroughly, right? Because it may happen there may be some tricks. So every time it may not be directly applicable. So you need to read the question twice before you are sure that whatever you solved that is the same is asked, right?
Yes, sir.
Okay. So once you are done with this, then you can go for this one. Here, consider steady one-dimensional heat flow in a plate 20 mm thickness with a uniform heat generation of 80 megawatt per meter cube. The left and the right faces are capped at constant temperatures of 160 degrees centigrade and 120 degrees centigrade respectively. The plate has a constant thermal conductivity of 200 watt per meter Kelvin. Right? So, can you try this one? So here,
Yes, sir.
yeah, it
Yes, sir.
is, yeah. So here it is 0.02 meter, right? This 20 mm is 0.02 meter, and you are having this 160 degrees centigrade temperature. Here it is 120 degree centigrade. Right, so the location of maximum temperature within the plate from the left face you need to calculate, and maximum temperature within the plate in degree centigrade is. So these two things you need to calculate. So and you need to go for that differential equation which we have discussed. Can anyone tell me which case is going to be applied? It is 1D, right? Yes or no? Hello? Hello?
Yes, sir. Actually, my phone was not working properly. Yeah, got it.
It is 1D, right?
Huh.
So, what else is clear from the given data? As these temperatures are kept constant, right? It means it is
Hmm.
steady state flow of heat, yes or no?
Huh. D to t
Yeah.
by dx2 plus q to the power n by k equal to 0.
Yeah, you will have d2t plus dx2 plus qg by k equals to 0, right? Or we have written that this whatever g, right? Yes or no?
Mm-hmm.
So now this heat generation is given as 80 megawatts. So if you write it in terms of kilowatt, then you can have this dt upon dx square plus this 80 into 10 raised to 3 divided by 0.2, right? Because you can calculate sorry that this k is provided 200 volt per meter cal, right? And we are considering in kilowatt, so I am writing 0.2. Clear? Here it is in megawatt, and here it is in watt only, so I am converting it into kilowatt, and here also converting to kilowatt. Are you getting?
Yes.
So this is
5 millimeter.
yeah, 1 second. Yeah, 5 millimeter is correct answer. Let us see how you will get that. So d2t upon dx square, or d square t upon dx square plus 400 into 10 to the power 3 is equal to 0. Now if you are going to integrate this, if you are going to integrate this, if you are going to integrate this, then you will get this dt by dx plus 400 into 10 raised to 3x is equal to c1. Now again if you are going to integrate, then it is t is equal to, or let us write in terms of this only, whatever, it's t plus 400 into 10 to the power 2 x square by 2
सर
is
टू
equal to c1x
सेकंड प्रॉब्लम का
plus,
आंसर 165 होगा क्या सर?
yes, yes, correct. So here this t can be written as this t plus 200 into 10 raised to 3 x square is equal to c1x plus c2. Now c1 and c2 constant we can have from boundary condition. So at x is equal to 0, t is equal to 160 degrees centigrade. So t is 160, right? And if you put x 0, then c2 will be 160, right? c2 will be 160. Now at x is equal to 0.02, t is 120. So at x is equal to 0.02, t is equal to 120. So if you put that 120 equal to this 200 into just 3, here actually it was plus, sorry, 120 plus, right? 1 second. Here it is 120 plus 200 into 10 raised to 3 into 0.02 square is equal to the c1 into x, that is 0.02, plus c2 160 we have calculated. So if you find c1, then it is 2000. Yes or no? So if you put all this value in that equation, then you will get t plus 200 into 10 raised to 3 x square is equal to 2000x plus 160. Now condition for maximum temperature is this dt by dx should be 0. So if you apply this into this equation, then you will have your x, I am not writing full, you can directly calculate, x will be coming 0.005 meter, so 5 mm. And if you put that x is equal to 5 into that equation, then your T max will be coming 165 degrees centigrade. Yes, is it clear? Right?
Yes.
If you put this,
Sir, please repeat these solutions.
sorry.
Please, can you repeat this solution?
Yeah, in this, if you are going to do this dt by dx is equal to 0, then this dt by dx is equal to 0 will give you this, what we can say, this 200, right? Actually, it is 2000, right? Here this 2000 minus, actually I guess this 2x into 200 to 10 raised to 3, right, equals 0. So this will give this x is equal to 400 to 10 raised to 3. It will be in denominator, right? Because this 2x term will go on the other side, and then it will be 2000 upon this 400 into 10 raised to 3. Yes or no? So it will be
Yes, sir. How we form that
1
equation?
by 200. Is it clear now?
I was asking how we form that equation t plus something that.
That equation actually we have already written, right? This equation we have received or we have derived, right, from the differential equation of heat transfer in 1D. After that we have applied these boundary conditions, at this x at x is equal to 0 and at x is equal to 0.02, we have applied this boundary condition in order to calculate this C2 and C1, and then we have put those values in this equation. So we have come to this equation. Is it clear now?
Yes.
Okay, so once you find this x, then you can find the maximum temperature by putting that value in that above equation. Is it clear to all now? Hello?
Yes, sir.
Yes.
Okay, okay. So now last question. A pipe of 25 mm outer diameter carries steam. Heat transfer coefficient between the cylinder and the surrounding is 5 watt per meter square Kelvin, and it is proposed to reduce the heat loss from the pipe by adding the insulation having a thermal conductivity 0.05 watt per meter Kelvin. Which one of the following statement is true? Can you try?
Yes, sir.
Hmm. So what you are going to do is you are going to calculate the critical radius of insulation.
Sir, 3.
Adding insulation will reduce the heat loss, right?
Yes, sir. Like heat exchanger, we did the same process, right, sir?
Sorry?
For heat exchanger,
Heat exchanger?
yes, sir. In thermal power plant,
Yeah, yeah, yeah.
due to heat loss, we generally.
Mm-hmm. So, for now, if you have calculated this critical radius of insulation, that is K by H, then it is 0.05 divided by 5. So, it must have come this 0.01 meters. So, it is 10 mm. Yes or no? Everyone is getting this right?
Yes, sir.
And outer radius of pipe is given as 25 mm. So whatever insulation you are going to add will be anyway greater than this critical radius of insulation. So heat loss will be reduced, right? Because you remember
Yes.
that graph, right? It will go up and then it will go down, right?
Uh,
After this critical
uh,
radius. Yes or no?
yes, sir.
Right? So you can have this graph, right, for this Q and this particular can be modified. Right? So in short, you got idea, right? This Q there. Okay, so C will be the correct answer.